Hey everyone, back in a new awesome video, and today we're going to continue with our series about classical mechanics. Today we will introduce moment of inertia. This quantity arises when trying to understand the kinetic energy of a rotational body. We will introduce it, and also we will see some useful ways of calculating it, such as with the parallel axis theorem, and we will also prove that theorem. So let's start. Right, let's try and see what the kinetic energy of this rotating body would be. This is a flat disk, and we're just going to take a small chunk of mass over here, delta mj, and this is going to be at a distance r from the rotational point. Now, we know that our moving velocity w, that is in the k-hat direction, equals d theta dt. Now, if we multiply the radius by our angle, what we're going to find is a path length, because that's how radians are defined to be. Therefore, if we do the same with our angular velocity, this r times w, what we're going to find is our regular velocity of j, in this case, rj, wj, well, and the angular velocity is really the same for all of them, so we'll erase that j. Now, we can try and express the kinetic energy of this small chunk of mass. The kinetic energy would be 1/2 times the mass, delta mj, times the velocity squared, which is going to be rj squared times w. Now, we would like to sum up, because this is the kinetic energy of j, so for the total kinetic energy, we would like to sum up all these small contributions. Notice we could have a similar situation over here. This is a top view, and this is like a side view, kinda. So we would like to sum up all of those, and our total kinetic energy would be the sum of j of delta mj rj squared, and we will have a 1/2 up front and w, which is constant. Now this sum is quite a bit chunky, I guess, because not all of the points from this small chunk we have chosen are the same distance, they are not moving with the same velocity, therefore, so we would like to reduce this to a minimum. And in fact, that's what it does when we take the limit as delta mj goes to 0 of this quantity of the sum, delta j, delta mj, rj squared. And what happens is that we end up with an integral of r squared in dm. Now this is going to become an integral of r squared times our density. We're going to have, imagine it's a constant density that doesn't depend on anything, times our area element. And we could use our knowledge about different things to find this. In this case, we would have to substitute our area element for polar coordinates, and we would have from zeta equals 0 to 2 pi, and from r equals 0 to the radius of this, we're going to take capital R of the density delta r squared times r dr d theta. Don't worry if you don't yet understand this, because this is multivariable calculus, and in the future I may make some videos about it. So it's only for the curious ones, we're making a double integral, first with d theta, with these limits, and with the dr. They are not related. We can take the d theta and do this integral, which will give us 2 pi times the density, and then we have a normal integral, r cubed, that's going to give us big R 4/4. And we find that this quantity is r to the 4 pi over 2 times the density. Now, this quantity is going to appear a lot, this one over here, this kind of integral. And taking into account, this is going to be the distance from the axis. Therefore, we're going to define that quantity called the moment of inertia. It's going to be represented with an I from inertia of the axis S. And this is going to be defined to be the integral over all the mass, and we're going to be integrating the vector to the axis squared. And this quantity is going to be really important. Furthermore, it is accustomed to express the moment of inertia in terms of the total mass. So usually, for example, in here, we know the mass is going to be the density times the area, so pi r squared times this. So we would express, in this situation, Is as r squared over 2, everything that's left, times pi r squared delta, which is exactly the same as the mass of the object. And this is usually how we express this new quantity, the moment of inertia. Wait, now let's explore the parallel axis theorem. Usually, we have lots of formulas for the different situations and different bodies, the common bodies, for the moment of inertia around their center of mass. However, sometimes we may want the moment of inertia around this axis, right around here, and we'll call it S, for example. And we don't necessarily need to know how to calculate those double integrals to find that there's much more easier ways. And that is with the parallel axis theorems. This theorem states that the moment of inertia around any axis equals, around any parallel axis, equals that of the moment of inertia through the center of mass of a parallel axis, so these two axes needs to be parallel, plus the distance squared between the axes times the mass of the object. That's why it's also custom to express it in terms of the mass, because that way it's easier. So imagine we know that the moment of inertia around the center of mass, on the axis of the center of mass, is L squared over 12 times the mass. In that case, we can easily find this value of the moment of inertia over here, because we know this distance is going to be L over 2, as it's 1/2 of the whole distance, and we're going to assume a constant density over this rod, and then I, it's going to be equal to this L squared over 12 times the mass, plus this, which is L over 2 S squared times the mass. This is going to give us an L squared m 1 over 12 plus 1 over 4, taking the common factor out. And now we can simplify this and find this is going to be 1 plus 3, 12, which is 4 over 12, and it's going to give you 1 over 3. So the moment of inertia is going to be L squared m over 3. And instead of having to do complicated integrals along the whole mass and taking into account lots of things and distance and everything, you have pretty easily found this value thanks to the parallel axis theorem. Alright, this parallel axis theorem is great, but you may wonder that it's too magical and where does it come from? So that is what we're going to prove now. So that's what we are going to prove now. Imagine we have a rigid body, this is the center of mass, we have our axis, the parallel axis, which the two axes for this moment of inertia, and we have, for example, this small mass element right over there. if we try to find the distance to this element from the other one, which we're going to call Rs, we find this distance to be Rs equals d plus r center of mass. Now we're going to be interested in this distance squared. Therefore, we will find this to be, and we're going to square it directly. We're going to have a d squared. Now we're going to have an RCM squared, and we're going to have the crossed element, the cross product, 2d RCM. Now, this moment of inertia is going to be equal to the integral over the mass. It's going to be a double or a triple integral, it depends, of Rs squared. And we can divide this into 3 different integrals. We're going to have the first one, which is going to be dm d squared. The second one, in which we're going to have 2, I'm going to write this second one, dm times drcm. And we're going to have the third one, double integral dm. We're running out of space, but right in time. Now, you may recognize some things over here. First of all, is that d squared doesn't change. It's a constant. Therefore, it can go out of the equation, out of the integral, and we may have m, the total mass, if we're integrating over the total mass, so we're going to arrive to this result, times our d squared. Now, next thing is that over here, we have the integral over dm over rcm. And this is no other thing than the moment of inertia around the center of mass. Therefore, this is equal to IZM. And we already have these two parts, so everything seems okay, but we have an extra term over here. But notice one thing, and that is that d goes out of this equation. And if we integrate around all points, if we sum all the points d with their masses and multiply them by their position with respect to the center of mass, by definition of the center of mass, that is going to give us 0. Therefore, this is just going to be equal to 0. And just like that, we have proven the parallel axis theorem. It's a very powerful theorem with a very simple proof, and it's really, really helpful. That is all for today. I hope you understood more or less how this moment of inertia is related, and also get a sense that, as we will see in the next videos, it's going to be like a mass, an inertial resistance, which is what mass does, in circular motion. So if we had force equals ma, now we're going to have, as we'll see in the next video, torque equals the moment of inertia, I, as the mass, times the angular acceleration. So it will have this analogous role as mass, but in circular motion. Furthermore, I also hope you got a sense of how to calculate it and the different tools you can use to your advantage. Remember that any doubts left, you may ask them in the comment section, and I'll try to answer them in the best way I can. Remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!